Hello, welcome to the course SJPHY1C01 Properties of Matter and Thermodynamics. The contents of today's lecture is taken from Heat and Thermodynamics by Brijlal and Subramaniam. We will continue to discuss topics from Module 3, Thermodynamics. Today we are going to analyze work done during a thermodynamic process. So imagine that you have some gas enclosed in a cylinder with a movable piston of base area A as shown in this figure. Let P be the pressure of the gas and V be its volume. And if the piston is displaced by a distance dx, what is the corresponding work done? So work is force into distance. So for a displacement of dx, work done dW is going to be F into dx. And pressure is force per area. So I can write force as pressure into area. So dW is PA dx. Area into distance is volume. So A dx is going to be the change in volume dV. So dW equal to PdV. Remember, always work is associated with a change in volume. Okay. So if the volume changes from V1 to V2, then the total work done is going to be integral of dW. Apply the limits. This is integral V1 to V2 PdV. So an important point to remember is here that the work done is a path dependent function. So it doesn't much depend on the endpoint. Instead, it depends on the path taken by the system to change from the initial state to the final state. Let's now calculate what is the work done in a quasi-static process, an extremely slow process. There are two types of quasi-static processes. One is a non-cyclic process and other one is cyclic process. Non-cyclic, as the name suggests, system moves from an initial state to a final state, and these two states are completely different. So imagine that you have an ideal gas undergoing quasi-static non-cyclic process represented by line AB in the PV diagram, and here you can notice the volume changes from V1 to V2. So how do you calculate the work done? You know, work done is nothing but area under the PV curve. So you take a small section whose thickness is dV, calculate the area under this. The area can be calculated by doing an integral under this curve, right? Now you extend your limits of integration from V1 to V2. This will give you total area under the curve AB, which is nothing but the work done. So work done is integral V1 to V2 PdV. Now what about a cyclic process? Here, as the name suggests, the system moves from an initial state to final state, but at the end of the process you will realize that the final state is same as the initial state. So the system returns to the initial state after undergoing a series of changes. So this is an example of a cyclic process. System starts from state A, goes through C, reaches B, then moves in the opposite direction. So through D, it finally reaches back the initial state A. So A, C, B, D, A. This represents a cyclic process. Now I can divide this into two halves. One is process ACB and second one is process BDA. So these two move in the opposite direction. ACB moves in the forward direction, BDA moves in the reverse direction. And the work done during process ACB, I call it as WACB, and from the PV diagram, this is going to be area under the curve ACB. Similarly, work done during the process BDA, this is WBDA, which is area under the curve BDA. Now here, since the system is moving in this direction, work is nothing but force into displacement. So if work is in this direction, it means that there is a force acting in the same direction. So If I take this as the forward direction or positive direction, this work is done due to a positive force, so I can call this as a positive work. On the other hand, in this case BDA, force is in the reverse direction, so I can consider this as a negative force which gives rise to a negative work. So WACB is the positive work and WBDA is the negative work. And what is the total work done during the cycle? Total work is sum of these two. So this is WACB plus WBDA. Since WBDA is the negative work, I put a minus sign here. WACB minus WBDA, which is nothing but area of the shaded region. This is the area enclosed by the cycle ACBDA. And when you compare internal energy and work done, there is a fundamental difference which I can highlight using the example of a cyclic process. So as I said, in the case of a cyclic process, system undergoes a series of changes and comes back to the same initial state. So if you calculate change in internal energy delta U is going to be U final minus U initial, and U is a state function. It depends only on the endpoints. But in the case of cyclic process, endpoints are exactly the same, which means delta U is going to be 0. On the other hand, work is a path function. It doesn't depend on the endpoints. Instead, it depends on the path taken. That's the reason, even though the endpoints are same in the case of a cyclic process, the work done is non-zero. So this is the fundamental difference between these two. One is a state function which depends only on the endpoints. One is a path function. It depends on the path taken by the system during a thermodynamic process. And we have learned that there are four fundamental types of thermodynamic processes: isothermal, isobaric, isochoric, and adiabatic. Let's calculate what is the work done in each of these processes. First, let's calculate work done in an isothermal process. As we already know, the product of pressure and volume is a constant in the case of an isothermal process. This is the famous Boyle's law. So you can call the constant as K. So if the system changes from an initial state P1 V1 to a final state P2 V2, then you can write P1 V1 equal to P2 V2. So imagine that you have 1 mole of ideal gas at a constant temperature T, which undergoes an isothermal change from the initial state to final state. And what is the work done? We know the general expression for work done, W equal to integral V1 to V2 PdV. This is the most generic equation, and using this equation we derive a specific equation pertaining to each of the processes. Okay. Now from this equation I can write P equal to K by V. So substitute for P, so you have integral V1 to V2 K by V dV. K is a constant, you can take it outside the integral. And what is the integral of 1 by V dV? This is ln V, natural logarithm. So K ln V, apply the limits V1, V2. This is K into ln V2 minus ln V1, which is K ln V2 by V1. Now from the ideal gas equation, I know PV equal to nRT, and if you consider 1 mole of ideal gas, PV equal to RT, we know that PV equal to K, so I can write RT equal to K, which means in this equation I can substitute for K and write RT instead. So work done during an isothermal process is RT ln V2 by V1. If you wish, you can convert this natural logarithm into base 10 logarithm by multiplying with a factor 2.303. So work done equal to 2.303 RT log V2 by V1. Once again, from this equation, you can see V2 by V1 is nothing but P1 by P2. So an alternate expression for work done is 2.303 RT log P1 by P2. Let's do a quick problem. 1 mole of gas at 27 degrees Celsius isothermally expands to double its volume. Calculate the work done. Given R, universal gas constant, is 8.3 joule per mole per Kelvin. Now, the first thing we have to do is write down all the parameters with appropriate units. Usually, we follow the SI unit system. But remember, when it comes to temperature, since we are considering absolute temperature instead of degrees Celsius, we have to write it in Kelvin. So temperature T is 27 degrees Celsius, which is 273 plus 27, that is 300 Kelvin. We do not know V1, V2 as such, but we know that since the gas is expanding, the final volume V2 divided by initial volume V1 is going to be 2. So that also we write here. Next step is writing down the relevant equation. Since the volume is given, we choose the equation corresponding to volume. So W equal to 3.303 RT log V2 by V1. V2 by V1 we know, T we know, and value of universal gas constant we know. Directly substitute in this equation, you get 1726 joule. So remember here, work done is positive, which means this is work done by the system. That's the reason why you are getting an increase in volume. On the other hand, if work is done on the system, externally you are applying a force onto the system, so system is going to get compressed. Okay, so positive work means there is increase in volume, negative work means there is decrease in volume. Moving on to an isobaric process, imagine that you have 1 mole of ideal gas heated at constant pressure so that its volume changes from V1 to V2. So as always, we start with the generic equation, work done W equal to integral V1 to V2 P dV. Since this is an isobaric process, pressure is a constant, I can take it outside the integral. So this is P into integral V1 to V2 dV. And integral of dV is going to be V, and apply the limits, I have P into V2 minus V1. PV equal to RT, so I can rewrite this equation in terms of the temperatures as R into T2 minus T1. Very simple and straightforward, right? Let's do a problem. What is the work done to change the volume of 1 mole of gas from 75 liters to 125 liters at 1 atmospheric pressure? First thing first, list out all the parameters in relevant units, mostly SI units. So pressure is 1 atm, but the SI unit is Pascal. 1 atm corresponds to 10 to the power 5 pascals. Volume is given in terms of liter, but the SI unit is going to be meter cube, and 1 liter is 10 to the power minus 3 meter cube. So V1 is 75 into 10 to the power minus 3 meter cube. And V2, sorry, there is a typo here, this should have been V2. V2 is 125 into 10 to the power minus 3 meter cube. Now write down the relevant equation. We have two equations, one in terms of temperature, one in terms of volume. Since we are given volume here, let's choose the equation W equal to P into V2 minus V1. And all the parameters are known, substitute here, you get 5000 joule. Once again, since the volume is increasing, this is a positive work done by the system. Next one, isochoric process. I think we don't have to do a great deal of mathematics here because this is very straightforward. In the case of isochoric process, volume is a constant, which means change in volume dV is going to be 0. So work done, integral P dV is going to be 0. So as I said earlier, work is always associated with a change in volume. If there is no change in volume, work done is 0. And last one, work done in the case of an adiabatic process. So in the case of adiabatic process, we know that PV to the power gamma is a constant, call this as constant K, where gamma is the ratio of Cp to Cv. So here, since there is no exchange of heat between system and surrounding, the temperature is going to be changing. So imagine that 1 mole of ideal gas undergoes isothermal change. Sorry, once again typo here. Undergoes adiabatic change from P1 V1 T1 to P2 V2 T2. Let's calculate the work done. As always, start with the generic equation W equal to integral V1 to V2 PdV and follow the same procedure as we have done in the case of isothermal process. From this equation, I can write P equal to K by V to the power gamma. So work done equal to integral V1 to V2 K divided by V to the power gamma dV. K is a constant, take it outside the integral. And what is the integral of dV divided by V to the power gamma? 1 by V to the power gamma, you can write as V to the power minus gamma. So its integral is going to be V to the power 1 minus gamma divided by 1 minus gamma. And V to the power 1 minus gamma, you can write as 1 divided by V to the power gamma minus 1. K remains as such. Now apply the limits. You get work done equal to K divided by 1 minus gamma 1 divided by V2 to the power gamma minus 1 minus 1 divided by V1 to the power gamma minus 1. We need to simplify this. We know that P1 V1 to the power gamma equal to P2 V2 to the power gamma equal to constant K. Now from the expression for work done, originally K is outside the bracket. You can take K inside the bracket. So work done equal to 1 divided by 1 minus gamma K divided by V to the power gamma minus 1 minus K divided by V1 to the power gamma minus 1. Now instead of first K, you can write P2 V2 to the power gamma. Similarly, instead of the second K, you can write P1 V1 to the power gamma. So you have terms involving V2 on both numerator and denominator. You can cancel that. So you are left with 1 divided by 1 minus gamma into P2 V2 minus P1 V1. We can simplify this even further. From the ideal gas equation, I can write PV equal to RT. So P1 V1 is going to be RT1. Similarly, P2 V2 is going to be RT2. So my equation for work gets modified as 1 divided by 1 minus gamma RT2 minus RT1. Take R outside. This is R divided by 1 minus gamma T2 minus T1. As I said, gamma is the ratio of Cp to Cv, and in the last class we have seen that Cp is always greater than Cv, right? This is the Mayer's formula. So gamma is going to be always greater than 1. So it makes more sense to write this equation in terms of gamma minus 1 instead of 1 minus gamma. So work done is going to be R divided by gamma minus 1 into T1 minus T2. Here T2 minus T1, here T1 minus T2. Now you can do an assignment problem. What is the work done when monoatomic gas at STP with Cv 10 joule per mole per Kelvin adiabatically compressed to double its temperature? So this is a slightly tricky problem because we know two equations to calculate the work done, but nowhere we have the parameters Cv. Instead we have R and gamma. So what we need to do? The equation which is written in terms of R and gamma, you need to rewrite in terms of C. So you can do that because you know the relation between gamma and Cv. You also know from Mayer's formula the relation between Cp and Cv. Cp minus Cv equal to R. Right? So from these two equations you can rewrite this relation. Then You have parameters T1 and T2, but there is no mention of T1 and T2 here. Instead, there are certain clues. One, the temperature is doubling. So T2 is twice of T1. And another thing is everything happens at STP, standard temperature and pressure. So you can look up the internet or any standard textbook what is the temperature at STP. So once you have all this information, you can plug it into the equation and get the result. Okay, so you can do this as an assignment. Before winding up, in the last class or in one of the previous classes when we discussed about isothermal and adiabatic processes in the context of indicator diagram, we have seen that both of them follow a similar shape, but the adiabatic curve is steeper compared to isothermal curve. And what is the physical implication of this? We know that area under the curve in a PV diagram represent the work done. So obviously area under the adiabatic curve is less than the area under the isothermal curve. So we concluded that work done in the case of adiabatic process is less than that during an isothermal process. Now we can give a mathematical proof to this. Mathematically we can prove that adiabatic curve is steeper compared to isothermal curve, or the slope of adiabatic curve is greater than the slope of isothermal curve. How do we do that? First, take the isothermal process. We know that PV is a constant. You take the derivative of this equation. So you need to apply the product rule. First function into derivative of second function plus second function into derivative of first function. So P dV plus V dP equal to derivative of a constant is 0. So now I can take the second term to the right hand side, P dV equal to minus V dP, or dP by dV equal to minus P divided by V. And what's the meaning of dP by dV? So if you have a graph drawn on the xy plane, this axis is x, the vertical axis is y, and you know that dy by dx is the slope of the curve. Now instead of y I have a pressure, instead of x I have volume, so dP by dV is nothing but slope of the PV curve, right? So slope of the PV curve in the case of an isothermal process is minus P by V. Let's now calculate what's the slope during an adiabatic process. We know that here PV to the power gamma is a constant. Take the derivative. So derivative of V to the power gamma is gamma into V to the power gamma minus 1 into dV. So plus V to the power gamma into derivative of P is dP equal to derivative of constant once again equal to 0. So the slope dP by dV equal to minus P gamma V to the power gamma minus 1 divided by V to the power gamma. So you have V term on denominator and numerator. You can cancel this. So you are left with minus P by V into gamma. So when you multiply the slope of isothermal graph with the factor of gamma, you get slope of the adiabatic graph. As I have said earlier, gamma is the ratio of Cp to Cv, Cp divided by Cv, and we know that Cp is always greater than Cv, which means gamma is always greater than 1. So you are multiplying the isothermal slope with a factor which is always greater than 1, which means the slope of adiabatic curve is always greater than the slope of isothermal graph. In other words, adiabatic curve is steeper than the isothermal curve, and concomitantly you will find the work done during an adiabatic process is less than work done during an isothermal process. So that's for today. In the next class we will discuss about the second law of thermodynamics, and one of the most telling applications of the second law or thermodynamics in general, that is the working of a heat engine. Thank you.